I have a great pleasure to introduce Patryk Lipka-Bartosik, whom I know for a few years. As a student, he was visiting us at Center for Theoretical Physics. He had an internship there with us. Later, he went to Gdańsk, yes, and now he is in UK working together with Paul Skrzypczyk. I'm not sure what is the correct pronunciation. This would be the Polish one. Yes,
yes,
it's a great challenge to pronounce this name in a British way. Yes. So, please, Patryk, tell us something about quantum thermodynamics and catalysis.
Yes, so thank you very much. And let me first start by thank you all for gathering for this talk. And I'm really, it's really a pleasure to give this seminar in front of such a great audience. So, today, as Professor Karol said, my name is Patryk, and I'm currently finishing my PhD at the University of Bristol under Paul's supervision. So this is a joint work with Paul, and if you are interested in the details, please have a look at the archive. So I will tell you about a certain property of catalysis, which holds in quantum thermodynamics, or if you prefer, we can view this more generally as a property of all majorization-based quantum resource theories. Okay, so let me begin by focusing our attention on a particular theory of classical thermodynamics. So this will be like our core idea, and then we will try to show how this generalizes. So in classical thermodynamics, the basic question which we address is of the following form. So we consider a system which has some Hamiltonian, and the system interacts with another system, which we technically call a heat bath. But in fact, it doesn't have to be a heat bath. So it's something which models our environment. In classical thermodynamics, we assume that this environment starts in an equilibrium state with respect to some temperature or inverse temperature, as I use this beta to denote the inverse temperature with some Hamiltonian. So, and the basic question which classical thermodynamics tries to answer is whether there is a transformation that, and under what conditions the transformation from rho to sigma may happen. And by transformation, I mean a thermodynamic process where an experimenter changes some knob or introduces some external fields to this system. And what classical thermodynamics answers, so classical thermodynamics answers this problem by invoking the notion of the second law of thermodynamics. So this is a particular one of the equivalent statements of the second law of thermodynamics, and it tells us that, well, when a certain function called non-equilibrium free energy decreases during the process, then such a spontaneous thermodynamic process can happen. And this function is it's a function which combines two different concepts. So first we have a term in this function f which corresponds to some equilibrium properties of the system. So we have here our standard textbook Helmholtz free energy, which generally when we solve some problem in thermodynamics, we just calculate derivatives with respect to this partition, to this function, and we can get some macroscopic thermodynamic variables describing the system. And we also have a purely information theoretic quantity here, the quantum relative entropy, which quantifies how far our state is from the corresponding thermal equilibrium. Okay, so this is the basic question studied by classical thermodynamics. So let me be a little bit more abstract. So I will denote this whole situation by saying that we have some free operation that takes rho into sigma. So by saying free, I mean that we have some heat bath and some thermodynamic process which takes our system and this heat bath to some other state. Okay, so this is the basic thermodynamic framework that we consider. So let me now be a little bit more formal and describe this this framework from a resource-theoretic perspective. So in resource theories, and in particular in the resource theory of quantum thermodynamics, which is sometimes also called the resource theory of thermal operations, we consider the following class of channels. So just to mimic the situation from the previous slide, we again start with a system, with our environment, and then to this whole composite system, we apply a joint unitary. And this joint unitary encodes the information about all possible interactions that can happen. So it may model, for example, how we exchange energy between these two systems. And then, since we are interested in precisely what happens on the system, we trace out all the information about the path. And this gives rise to a class of channels. And in fact, it's the most general class of quantum maps that we can have. So in order to focus precisely on thermodynamics, let me introduce a couple of additional assumptions. So the first assumption is I will denote this tau b with this tau b will be taken to be in fixed state, and the fixed state is that of the Gibbs form. So precisely, we start with some the path. This is really a path which starts in some with some inverse temperature and has some Hamiltonian. But we can choose different Hamiltonians here to generate different heat buffs. And secondly, we assume something about the dynamics, and in particular, we assume that so mathematically we assume that the unitary commutes with the total Hamiltonian, which physically means that the energy is conserved at every time when this process occurs. So this more technically, this means that this unitary, when we write it down in energy eigenbasis, it will have a block diagonal form, and inside each of those blocks we will perform a different transformation, which will definitely conserve the total energy. Okay, so with this we can now reformulate the basic question from the previous slides, and this is from a resource-theoretic perspective. We say, well, what we now look for is, given some input and some output state, we want to determine if there exists a thermal operation that can map our input into the output. So this is like the basic question which we want to answer. And it turns out that when we formulate a resource theory in this particular thermodynamic context, such a partial answer has been found. And by partial, I mean that we know we can characterize those transformations in the case where the input state is block diagonal in the energy eigenbasis. And it turns out that a relationship that captures this is the following one. So this is called a thermomajorization relation. And there are multiple ways of defining this relationship. So this is one of such methods. But for our purposes, if you haven't seen this previously, then it's not important. For our purposes, what is important is that you can type this into the computer, and this is a binary relation which tells you that, well, either this holds or it doesn't hold. So this also, at the same time, this defines a pre-order on the space of all density operators. Right. So one of the things which we would expect from such a microscopic theory is that it reproduces our expectations from macroscopic thermodynamics. Right. So somehow we would like to see that in an appropriate limit, this pre-order between states is the same order which is determined by the standard second law of thermodynamics. And unfortunately, this is not the case. So,
I'm sorry, Patryk, as you write that one curve is above another one, maybe do you plan to show us such curves and such examples to understand better this definition?
All right. So I don't have it. I can draw it if it's okay for you.
Yes. No, but look, if it's written that something is above something, it's good to understand and visualize what is above what.
Right. So let me check if I can draw something here.
Yes. Maybe you can use annotate.
Yeah, let me...
Yes, sorry to interrupt you, but maybe it will be easier for us to understand it more precisely. So look, there's view options at the very top, and then annotate.
Right. Yeah, I can see. Yeah, great. Yeah, I can see it now.
Yes, and maybe you could possibly help us to understand. Yes.
I clicked draw, but it doesn't let me draw. There should be some white space which should appear, but I can't see.
Maybe you can just try to write at your view graph somewhere.
Okay, if that is... Yeah, so,
well, just here.
Yeah. I mean, I try to do it, but if I click draw, then basically
No, but look, you can just draw a function and two functions. You just press draw. So
yeah,
you have yes, it works.
So I do it now, and it doesn't let me draw anything.
I can't see anything. Yes.
And maybe we have to allow the speaker to be able to annotate. Maybe not everybody has the
sorry,
right to
Patryk,
annotate.
sorry to disturb you. Maybe it's not so relevant. I was thinking it's easy for you, but no, if it is too complicated, let's postpone it for later. I don't want to take your time. Sorry.
Let's postpone this. So okay, maybe let me just very briefly clarify it verbally. So by saying that this one curve lies everywhere above the second curve, I mean that you can associate with each state, with each quantum state, a certain curve in 2D space, and if that curve, and if you look at each point in the x-axis, if the curve of one state is above the second, the corresponding point on the second curve.
Yes, but please remind me, what is the space? So you have a curve. What is at the axis?
Yeah, so at the x-axis,
yes,
the probabilities of the Gibbs state. So,
yes.
So this is like the x coordinates.
Okay.
And on the y coordinate, we have the probabilities of the state.
Okay. Okay.
Yeah. So maybe one addition, it's a cumulative probability distribution.
Okay. So it's almost like standard majorization.
Yeah. So the only difference is that you change what you have on the x-axis.
Okay. Yes, thank you. Sorry for the interruption. Okay, yes. Please continue.
Yeah. So thank you very much for this clarification. Okay. So let me proceed. So the problem with this approach is that we don't get standard thermodynamic expectations from this.
Hey, Patryk, can I ask you something?
Yeah, of course.
You don't reproduce macroscopic thermodynamics even in the case that rho and sigma are in thermal equilibrium, but with different Hamiltonians?
Yeah, because, I mean, so in those cases, so I would say that in a measure zero set of cases, you get this, like you get it if your state is a perfectly excited state of the qubit, for example, and in a thermal qubit state. But I would say that for general states, you don't get the same partial order.
Okay, thanks.
Can I also ask a question then? I mean, I think it should be maybe better explained. What does it mean does not reproduce macroscopic thermodynamics? I mean, because for one of the ways that they show that this reproduces is taking many copies of systems and going into the asymptotic limit, because actually macroscopic thermodynamics concerns many particles, right? And then you can show that in many copies, when you take n copies of rho and n copies of sigma, then you can do this, right? So, I mean, if you could just specify what you mean by reproducing here.
Sure, yeah, so that's a very good question. So sorry for not specifying before. So I mean precisely this what you described. So by macroscopic thermodynamics, I mean that if we take the limit, the asymptotic limit of multiple copies, when we consider a large number of copies, like the IID limit, and then this particular relationship doesn't reproduce the standard second law. And so what generally we need to be able to, or maybe in other words, so this relationship defines a certain partial order on the space of all density operators. So by saying that it should reproduce macroscopic thermodynamics, I mean that if we take the IID limit, so we consider asymptotic transformations, then this partial order should collapse when order governed by the free energy. the non-equilibrium free energy in the general case.
Yes.
And so basically what can be shown, and it can be shown that there is a way in which we can reproduce this limit, so we can see this second law emerging from the theory. But what we have to do is generalize this theory a bit. And what so perhaps the paper that you were referring to, so is this paper. So what they essentially do is they allow the experimenter for some additional freedom. And the freedom they allow is basically to consider catalytic version of those thermal operations. So the basic idea is that now not only we consider transforming our state using a heat bath, but we also allow the experimenter to borrow another quantum state, which also takes part in this transformation, so interacts with the heat bath and the system. But we are also constrained to return the state in a perfectly undisturbed state. Right? So in this sense, the transformation is catalytic, meaning that if we borrow omega, then we have to return it in precisely the same state. And it turns out that precisely in thermodynamics, this gives additional power. So in other words, there are transformations which cannot be, where you can't just directly transform from rho to sigma, but if you use a catalyst, then you suddenly can. Right, and so and this is precisely this way in which you can reproduce those macroscopic predictions, at least in terms of the second law. Okay, so this extension is fairly general, so we don't need to constrain to thermodynamics in this case, so we can consider arbitrary resource theory and allow for such additional possibilities. And our basic question of this resource theory can be now reformulated. So now we not only ask about whether there is a thermal operation, but we now also ask if there is an ancilla such that the following transformation can happen. And it turns out that, so this is precisely this result which reproduces the thermal macroscopic predictions. So for block diagonal states, we know that these two things exist, so a thermal operation and some ancilla, if and only if the following set of conditions is satisfied. So you can view this from a more general perspective as a complete set of monotones for this catalytic resource theory. And maybe from a more physical point of view, this can be viewed as some generalization of the second law of thermodynamics. So one way to see this is, well, let's write down this what this function f alpha is. And as we can see, it has a form very similar to the non-equilibrium free energy. So here we have this Helmholtz term. And here we again have an information theoretic term, where now the difference is that we replace the quantum relative entropy with the so-called sandwiched Renyi divergence. So this is quite a complicated quantity, which may be difficult to compute in certain cases. But for our purposes, since we are interested in block diagonal states only, we can simply write down this quantity in the following way, where Pi are the occupation probabilities in the energy eigenbasis of P, and Gi are the corresponding ones for the thermal state G. Okay, so one way to see second law from here is, well, if we take alpha equal to 1, then this quantity here becomes just a quantum relative entropy, and we would see that this is basically the second law statement. However, this is an infinite family of conditions. Therefore, it's the partial order determined by this set of monotones is more complex than the standard one. All right. So, well, these are the second laws which were found, and which completely describe the possible transformations in this resource theory, and hopefully they allow to reproduce these macroscopic predictions in this precise sense, where our goal is to somehow see the second law of thermodynamics emerging from this partial order. And to see this, we can more precisely look at the following transformations. So we look, so So suppose that our goal is to transform n copies of rho into n copies of sigma, potentially using some catalyst to aid the transformation. And from using some mathematical properties that those Renyi divergences or generalized free energies satisfy, we can infer that the following limit, when n is sufficiently large, basically collapses to the non-equilibrium free energy. And I'm saying basically because, well, to make this statement technically correct, we still need some technicalities like smoothing of those functions, but let me not describe that for the purpose of this talk. All right, so for our purposes, what is important is to note that the second laws of thermodynamics, this is how they are basically called in the literature, they collapse to a single second law in the case of asymptotic transformations. So this is precisely the sense in which I'm saying that this theory reproduces standard thermodynamic expectations. Okay, so with this, let me make a small digression about catalysis in general. So it turns out that it is quite important how we allow for an error, how we quantify any disturbances that occur on the catalyst. So in the ideal world, what we would like to have is a notion of catalysis which is free from any errors. But in reality, if we were to implement the unitary or use some state, some actual state in the transformation, then nothing of those things can be prepared with perfect certainty. So any error that can happen on the catalyst, errors happening on the catalyst are inevitable. And this means that we should have some way of quantifying how this catalyst can be disturbed. And let me define this error in the following way. So this is just, we look at the reduced state of the catalyst and we check how much it differs from the initial state. And this naturally leads to certain classes or regimes of catalysis. And the first of such regimes is the regime of exact catalysis, in which we do not allow for any error on the catalyst. And in the same time, we do not allow for building up correlations between the system and the catalyst. So this is the standard case for which those second laws of thermodynamics hold. Secondly, we have a case of correlated catalysis, where basically, again, we don't allow for any error on the catalyst, but in the same time, we allow for building up correlations between the system and the catalyst. And those correlations can be arbitrarily large. Finally, we have the case of approximate catalysis, where we now allow for some error on the catalyst, but in the same time, we demand that the correlations vanish. The correlations between the system and the catalyst vanish. And by vanishing, I mean that we have a way of making those correlations as small as 1 pieces. For example, at the cost of increasing the size of the catalyst. All right, so this third case is precisely the case which we will be considering in this talk. However, there's still one more challenge to overcome. So precisely because of this relaxation here, we have to be sure that we are not falling into the problem of embezzlement. And embezzlement is a situation where one allows for an error on the catalyst, and in the same time, the partial order completely collapses. And such a thing can happen, for example, if we treat the catalyst as a sort of a battery or an entropy dump or an entropy sink. So this is something which we have to assure we don't do. And still, there are some examples which tell us that even though the error on the catalyst can be made arbitrarily small, so the error goes to 0 with the size of the catalyst, let's say, and in the same time, the partial order determined by those transformations, it collapses. And intuitively, this means that somehow that this trace distance does not capture properly the amount of resource that we have in our system. So we can disturb the state ever so slightly, but in the same time, the resource cost of fixing the state back to its initial state can be enormous. And hopefully for our purposes, this precise problem has been studied in this paper. And what the authors have found was that you can find a bound, it's called an embezzlement bound, such that when your error on the catalyst is smaller than this precise value, then no catalyst can ever collapse this partial order. So the resource theory is non-trivial in that case. When the error on the catalyst is larger than this threshold value, then basically you can find the catalyst state such that any state transformation becomes possible. Right. So what we have to assure in this, for the purpose of this talk, is that we are always our error on the catalyst is always smaller than this embezzlement bound. So here the S corresponds to the dimension of the system, dc is the dimension of the catalyst, and n will denote the number, well, the logarithm of the dimension of the catalyst, or in other words, roughly speaking, the number of particles comprising the catalyst. So what we have to make, what we have to assure is that our error scaling on the catalyst is better than 1 over n, and this will imply that we can get arbitrarily far from this embezzlement bound. Okay, so with this, let me get back to the problem of catalysis again, and from a resource-theoretic perspective. And so in particular, we know that those second laws of thermodynamics imply that there exists some catalyst. However, a priori, we don't know anything about that catalyst. So we don't know anything about its Hilbert space, its dimension, its state, its energy content. All of those things are somehow have to be determined. We only are guaranteed existence of such a catalyst. So this leads to a certain problem. The most natural one is how we should determine such catalysts. How should we approach to finding them? And secondly, perhaps it would be quite interesting to study how special are such catalysts. So for example, if I want to use a catalyst in my particular transformation, then it will be quite useful if I could use this catalyst in some other transformation. In other words, how finely tuned must those catalysts be? And it turns out that if you take a random paper of catalysis, then what the authors generally do is that they take a very particular catalyst and then they show the results so that this particular catalyst does the job, but you can't directly take this catalyst and check other properties of the system or of the transformation with it. So this gives something like a folklore knowledge that that catalysts have to be very finely tuned for the particular transformation. And with this, we arrive at the main meaning of our work. So what we basically show here is that any state, given that it is provided to us with sufficiently many copies, can act as a catalyst for all transformations that are allowed by the second laws. So not only any state, any multi-copy state can be a catalyst, but also it can be a universal catalyst, meaning that it can catalyze all potential transformations. Okay, so this is something I will describe in a moment in more detail, but with this, let me highlight one more thing. So somehow so far I have described catalysis as a way of amending the resource theory of quantum thermodynamics. However, I believe we can think about catalysis in a more general terms, and in particular, we can think about catalysis as a way of extending the standard QRT framework, which somehow allows us to find or finding the ultimate limits of such resource theories. So just like we had with thermodynamics, this thermodynamic limit and the free energy, the partial order governed by free energy could emerge only if we allowed for those catalysts, then perhaps a similar situation can happen for other resource theories as well. Okay, so with this, let me highlight very briefly a couple of numerical results. And the motivation is that this is something which we start with. So, and we have seen some nice numerical properties of, well, you can view this as properties of majorization in general, which we couldn't prove. So we had to resort to some to specify some more assumptions, and this gave us access to some analytic results. However, the numerical case is still open. So let me briefly mention this. So let me imagine the following experiment. So suppose that I consider a very particular state transformation, and so I have a state rho as star and some state sigma as start. So I want to transform rho into sigma. So what I can do is, well, if I'm working in the resource-theoretic thermodynamics, then basically the only relevant information that I have to extract from that state is its energy distribution. So these are the occupations in the energy eigenbasis of my initial state, and these are the associated occupations of my final state. And now I can compute those second laws, so I can calculate those generalized free energies for those states. And what I would see is basically that the free energies of P star are always greater than the same quantities calculated for Q star. So this implies that there is a catalyst which can activate this transformation. However, if we were to compute this thermomajorization criteria, what we would see is that P star can never be transformed into Q star. So this clearly shows that, so this is an interesting case in which we know that there exists some catalyst, but we are sure that trivial catalyst will not do the job. So we have to really find a catalyst which can activate this transformation. And we try to find such a catalyst, and it turns out that, well, doing it analytically is quite difficult. What we did is basically we tried to check, well, does a random catalyst, is a random catalyst useful for this transformation? Will it help to perform it? Okay, so.
Sorry, short remark or question. So look, beta is this parameter which represents temperature, or 1 over beta, yes?
Sure.
So in the remarks here, is it valid for any beta or for some concrete values of this temperature parameter?
Right. So that's a very good question. So I should have started before. So sorry for that. So essentially, beta is fixed once and for all. So when we define our resource theory, then we fix the temperature. So all those statements are valid for this one particular beta.
Okay, so you're for fixed beta, but you don't vary, you don't change beta.
Yes, we don't change beta. It's fixed.
Because you may also ask how the situation changes if you change temperature, but you don't do it here.
Right. Yeah. So it's I would say an orthogonal question.
Okay. Okay. Thank you.
Yeah, because if you wanted to change the temperature, then you need access to other thermal baths, and it's basically it can be difficult.
Well, you could have or you change temperature of the bath, which makes sense. Yes.
Yeah. If you have some.
Okay.
No. Yeah.
Thank you.
Yeah. Thank you. Okay. So basically, to try to find such a catalyst, what we can do is, well, we can choose it randomly. So we can randomly, and because we are precisely interested in the energy distribution, then what we do is we just choose a random state from the simplex. So there's one preferred basis, the eigenbasis associated with energy. So we don't have to randomly choose the phases. So basically, we just choose probability distribution to be the catalyst, and we fix some error on the catalyst. And we have to assure that this error is small enough so that we are deeply inside this embezzlement bound. And then we basically check if this particular catalyst that we randomly drew can be used to activate this transformation within a small error. And what we basically would see if we did this numerics is, I would say, quite surprising. So this is the following plot you would get if you just try to estimate this probability of success. So for example, if the size of our catalyst is just 16 or 4 qubits, and if we plot on the x-axis the allowed error on the catalyst, and on the y-axis we plot this probability that a random catalyst is useful, what we would see is essentially that this probability very fast approaches 1. And if we increase the dimension of the catalyst, so if we increase it by adding just 2 qubits, then we would see that this this probability will really briefly, quickly approach 1, and within even a smaller allowed error. So all these plots are generated when the embezzlement bound is behind the plot scale. And and basically these are, the inset shows an exemplary distribution of the eigenvalues of the catalyst. So basically for the dimension 256, these are the this is the histogram of all the eigenvalues of the catalyst. And so this is an exemplary one drawn from exponential distribution. So this probability will very quickly approach 1. So I would say the modest conclusion we can draw from this is that there are some transformations. At least there is at least one transformation for which random states can act as catalysts with high probability. And it turns out that you can be more general, and the same statement can also hold. So if you consider not this fixed transformation but arbitrary transformation, then you can show that you have a similar behavior. So which holds universally, right? So a random catalyst is not useful for a particular transformation, but for all possible transformations as well. Right. So if you are interested in this numerics, then please have a look at the paper. So where we expand on those numerics. But for our purposes here, the important bit is to understand this, and why does it really is it the case that random states are useful catalysts? And we couldn't answer that question. So what we basically did was we lowered our expectations. So we assumed that the state of the catalyst has a multicopy form. And by this, I mean that we now take an arbitrary state and assume that this arbitrary state, is supplied to us with sufficiently many copies. Right? So, and the formal statement of this, the formal statement is the following. So basically, so this is the main result. So given some state rho and sigma, which are block diagonal, and if those states satisfy the respective second laws of thermodynamics, then for any catalyst state omega and sufficiently large number of copies of that state, the following transformation may happens. So we can take, so rho goes to sigma, and in the same time, the catalyst, the n-copy catalyst, is transformed into some other state omega c prime. And this omega c prime, it is a state which is epsilon c close to our initial state. And what we assure at the same time is that this error, this epsilon c, scale is better than 1 over n, which effectively means that we can, by increasing the dimension of the catalyst or increasing n, we can make this arbitrarily far from the embezzlement bound. Okay, and the proof is, let me just very briefly sketch the proof, give you some idea of why this really holds. So the proof is by proposing a certain protocol which does the job. And the protocol consists of our system here, the n-copy catalyst, and the heat bath. So from the heat bath, we draw two states. So this is still one single heat bath, but for simplicity of presentation, I chose to describe it in two places, to just say that we use two different copies of the free state. Okay, so with this, let me now specify the protocol which performs this transformation. So we start with some preprocessing step, which acts on the catalyst and the path. Then we apply our actual catalytic transformation, and then there's a post-processing step. So maybe one comment in place is that if this unitary V does not change the catalyst, then essentially here on the catalyst and the heat bath, we essentially apply an identity map. So nothing changes here if V doesn't do anything with omega c. And the idea behind this U and U dagger is that this unitary U, in some certain sense, encodes the information about the transformation. So it encodes the information about rho and the desired state sigma in this n-copy catalyst. V does something with this encoded catalyst, this catalyst which encodes the information about transformation, and then we decode the catalyst back so to return it to its initial state. Okay, so let me specify these 3 steps now. So in the first step, what we do is basically we perform a multi-copy conversion, and technically, for our purposes, what turns out to be extremely useful is the following result from Kamil's paper. So we essentially want to transform this n-copy catalyst into some fixed state, which now encodes this information about transformation. And this can happen with a sub-exponential error on the catalyst, right? So when n is the number of copies of the catalyst, then this is the error with which this unitary is applied. And this is therefore also much smaller than this 1 over n bound, which we have to be careful about. Okay, and so it turns out that the state which we have to use here, so which we want to encode our information using it, is the following state, which we refer to as the Duan state, which was, to the best of my knowledge, used for the first time in this paper. And the basic idea is that it's a classical quantum state with a classical register of size, say, k, and a suitably chosen combination of input and output state. Okay, so just to make to gain some intuition, if k of the size or the size of the classical register is 3, then we have the following form of this Duan state, and I will use the following graphical notation. So on the x-axis, I will denote the labels of quantum systems. So this is C1, the first catalyst particle, the second catalyst particle, and on these y-axis, I will denote the classical registers. So the blue blob will correspond to the input state, and the red blob will correspond to the output state, sigma. Okay, so
sorry, just a second. Could you please show it again? So eta 3, it is a number or a state?
So eta 3 is a state. It's a quantum state.
Okay. So, but why it is 1/3? So state is equal to 1/3? No, because you have an object like a state, and here at the very end it's written 1/3.
This is pictorial representation of the state. The color pictorial representation of the state.
Mm-hmm. Yeah.
Yes, of course I see pictorial representation, but I'm a bit confused with the equation that eta 3 is equal to 1/3.
No, it's 1/3 times this
multiplied.
Ah, okay. Sorry. Okay, there's a bracket. Okay, now I see. Okay, sure.
Yeah.
1/3 times this object. Okay, sorry. Yes, it's clear. Yes.
Yeah, so I should have made it.
Okay. Maybe having here a bracket would help me. I would not make such a mistake. Sorry. Yes, it's clear.
Yeah.
Yes. Thank you. Sorry for interruption.
Mm-hmm. Okay, so with this, this is the state somehow which we produce in this encoding procedure. And just let me mention one additional lemma which will be extremely useful for us now. So this is a lemma somehow adapted from this paper about majorization. So, and this describes as something somehow a little bit less known property of those complete set of monotones. So we know that once we satisfy those second laws, then we are guaranteed that there exists a transformation that takes k copies of rho into k copies of sigma for some finite k. This k can be large, but it's finite, and we know that so this is somehow a bit counterintuitive, because normally when we talk about those alpha free energies or Renyi entropies in general, they quantify some single shot transformations or properties, and here on the other hand they can also tell us something about the multi-copy regime as well. So for our purposes, it is important that those second laws, they imply that there is a multi-copy transformation that takes k copies of rho into k copies of sigma, right? And precisely this is what we use now. So let me assume for the moment, just to show how the proof looks like, that the k that is implied by those laws is free. So suppose it's just free, and then let's look at this composite system of the state rho and our preprocessed catalyst, eta K. So using this graphical representation, let me just use our system here. So this is the system which is tensored with the catalyst. So now, if we take this bar and we look at the joint state, what we would see is that on one of the registers, we can see a state which can now be activated using this unitary transformation from the lemma. Right, so 3 copies can be now activated into or transformed into 3 copies of sigma if we use a controlled unitary, where the control system is the classical register and the unitary applied is either identity or the V tilde. Okay, so this is the state which we would achieve. And then if we, well, then basically what we have to do is to do some relabeling or swapping. So what we do is we perform a cyclic swap on the classical register. So so the third the system in the third register, we turn it into the system in the second register. The second register goes into the first register, and the first register goes back to the third register. So this is, you can view this basically as a relabeling or swapping systems, swapping the classical register. And this is essentially the state which we would get from this procedure. And now we do a similar thing, but on the quantum register. And for simplicity, let me just change the labels and not move those blobs. So S gets swapped with C2, C2 gets swapped with C1, and C1 gets swapped with S. So this is basically the situation which we would get. And if we now trace out our system from this state, so we trace out this part of the composite system, what we would get is the following state. And as we can see, so this is precisely the state with which we started with. So this is the Duan state which we had initially, the state eta K for K equal to 3. And if we trace out the catalyst, so we trace out the classical register plus those those particles here, those quantum systems, what we would get is essentially the red blob, which is the state sigma, which we wanted to achieve. Right. So let me now finish this protocol by specifying what this inverse unitary does. And it is basically the same unitary which we applied initially, but applied backwards. So what it does is basically it turns this Duan state, which wasn't disturbed by V, into some other state, into our initial n copy state, up to some error. And if we were to calculate the total error of this protocol, what we would see is that it's twice the error induced by each of those unitaries, which is basically still sub-exponential in n. Okay, so with this, we can now combine all those steps, and finally we can trace out the buff systems. And what we would get is basically the following statement. So our hypothesis was that those states satisfy respective second laws, and as a consequence, we would see that n copies of any state, of course, as long as it's not the free state, so it has to have some amount of resource to be able to implement this unitary U. Otherwise, n would just need to be infinite and still wouldn't be enough. But then the following transformation can happen. So rho can be transformed catalytically into sigma, where by catalytically I mean this approximate catalysis sense in which error scales much better than the bound for embezzlement. Okay, so with this, let me now briefly summarize this talk. I hope I can convince you that we still don't understand much about catalysis. In particular, the dimension or the necessary amount of resource that the catalyst might have is still not well understood. In the same time, I showed you some numerical results which shows that generic large dimensional states make good catalysts. And finally, I told you that if we accept a multicopy form of the catalyst, then basically all resource theories that are governed by majorization, for example, quantum thermodynamics, in all such resource theories, every state is a useful catalyst for all transformations, as long as it is provided with sufficiently many copies. Okay, so with this, let me finally very briefly highlight a couple of open questions. So first, I believe it's quite interesting to, it would be quite interesting to understand why really those generic large dimensional states make good catalysts. So, somehow in my head, I think we know why multi-copy states can be useful, but the general case is still not well. I mean, at least for me, I don't understand it at all. Secondly, I think it will be quite interesting to see if a similar behavior of catalysts extends to arbitrary resource theories, not only those which are governed by majorization, but also to arbitrary resource theories. And it seems a plausible thing to have, because well, the methods which we use here somehow rely on a majorization in a very technical sense. So I think there's still a scope to make it general enough for arbitrary resource theories. And I guess the final question, which I guess for me in particular is the most interesting one, is that can we use catalysis for more practical tasks? So maybe not only thermodynamic, but arbitrary tasks in quantum information. So far, the intuition about catalysis is that it enables some transformations which were previously impossible to carry out. But the question is, can it also be useful to enable those transformations which find a particular application in quantum information? So if you are interested in this question, then we put online the following paper, where we essentially consider this problem in the case of teleportation. So it turns out that if you want to teleport a quantum state, then basically using a catalyst can help you. So teleportation is a very particular type of transformation in which you Alice and Bob share some state. So for the purpose of this talk, let's look at the following example. So let's suppose that Alice and Bob share a quantum state, an EPR pair, and the goal posed between Alice and Bob is to teleport the state, a Q-treat state, from Alice to Bob. So it turns out that a standard benchmark for assessing quality of teleportation is called average fidelity of teleportation, and you can easily compute this quantity easily, at least numerically, you can compute it. And for this particular case, when Alice and Bob teleport Q-treats using an EPR pair, it is 3/4. So if Alice were sending Q bits to Bob, then she would do it perfectly, clearly. But if she wants to teleport Q-treats, then she can't do it she can't do it in a perfect way. So this is the fidelity she would achieve. However, it turns out that if you use a catalyst, then you can improve this fidelity of teleportation by roughly 13%, which I think is quite a reasonable advantage that catalyst offers. And the interesting thing is that somehow this improvement works in a way that you first improve the singlet fraction of a state, and then you perform teleportation using this reprocessed state. So how catalysis it can increase the singlet fraction of a state, meaning that potentially it can also be useful for other tasks which involve singlet fraction as the quantifier. Okay, so
and this number 0.85, it is only a numerical value, yes?
So this is.
Or is it analytical value?
So it's an analytical value for this particular example. So this is quite a simple example. So it gives so for this one can find quite easily an analytical value. Yeah, but in general, yeah, for other states, you need to solve a linear program to get the value.
Thank you. Mm-hmm.
Okay, so maybe I should thank you now, you all, for listening. And so with this, let me conclude this talk, and I'm happy to answer any questions you might have.
Yes, thank you very much. Congratulations for a nice talk and for finishing ahead of time. So let's open the discussion. We have plenty of time for discussions. So who would like to ask a first question?
I may have one question and one comment. If
Yes, go ahead, Kamil, please.
So they consider the errors. So you do as, because maybe I missed this, but you had some condition for the error of the catalyst, because obviously you can do some embezzlement if you allow the catalyst to differ too much, then you can break any kind of condition. So what was this condition on the, that you said something like of the order 1/n that somebody proved? Could you repeat this and clarify maybe a little more?
Right, okay. Right, so basically this is the condition. And so the basic idea is that, so in that paper, those guys, they find a family of catalysts. So it's a family of quantum states, such that if you use them as a catalyst, you can for example, let's fix just to the resource theory of purity and consider just majorization. So in that case, you can transform a maximally mixed state to a pure state by exploiting this catalyst. So you use a catalyst that they propose, and you are able to transform a maximally mixed state into a pure state of somehow breaking the catalyst up to this error. So this is the error they enforce. So and since well, you can, so since this is the most difficult transformation you can have, so transforming a free state into the most resourceful one is the most difficult thing you can have in that theory. Then they conclude that this basically that you can also do any other transformation, which we
But then this means that the error of the catalyst should at least be 1/n, not that if it is 1/n, then everything is going to be fine and no embezzlement will be there, right?
Yeah, so I would say that it means that if you allow for this error, then you are sure that there is a catalyst which can completely destroy your partial order.
Yeah, exactly. But if you make it smaller, you are not guaranteed that there won't be.
Yeah, I mean, if you make it smaller, if you make it smaller, so
because what I understood is that you in your protocol, your error was much smaller than this because it was exponential x to minus n to x. But does this guarantee that there is no embezzlement still?
Right. So yes. So sorry for that. Yeah. So you're sure. What they show basically in their paper is that this error is optimal. So yeah. So if you can embezzle the state, then basically with some error, then basically you can always embezzle it with a smaller error using the family of catalysts they propose. So in other words, if you find a state, so if we allow for a smaller error than this, let's say some epsilon prime, which is smaller than this, and you use it, then this would imply that if you use a different state than the one they propose, then yeah. So okay. Yeah. So basically, if you use an epsilon prime which is smaller than this bound, then you can check, well, if I use their catalyst, can I do this? It turns out, so if you can't do the transformation using their catalyst, then you have to find a epsilon c. Sorry, I'm mixing things up.
Okay, let's not worry. We can discuss about that because this is I think in crucial important detail. But maybe we can discuss this afterwards. I can
yes,
dissolve the discussion.
Yes.
But then the second
yes.
Just a second comment. It's gonna be a quick one. So I just think it's maybe not perfectly fine to because I was waiting for your set to hear your setting, but because your setting also has an error, I think it is a little unfair to say that this original result does not recover the macroscopic result, because in the asymptotic limit, you can show that if you allow for arbitrarily small error of transformation, so your final state is arbitrarily close to your target state, then you recover the second law of thermodynamics in the standard macroscopic case, which with just one free energy functional. So so maybe just a comment that that's not exactly, because people who devised this, they exactly wanted to have the asymptotically to recover the original second law, and they did recover it by just putting a little bit of error, as you do in catalytically.
Yeah, yes, that's a very good question. So I would say that the problem here is in the way in which we so it's all about how the error scales with this dimension, right? So the result which you mentioned, so I guess this is in this reference 5. So what they basically show is that if you consider an error which scales like 1 over n, so this is precisely on this bound, then what you get is the free energy, right? So when you allow for an error which is precisely of the order of 1 over n on the catalyst, then the only surviving monotone of that theory is the free energy, right?
Well, I'm not sure how was it in the paper by Brandau, but the paper that you cited by me with the moderate deviation, it definitely we had the errors of e2 minus nx, and it was only the free energy surviving. So if you allowed the error to go like e2 minus n to power x, then the only relevant monotone was free energy. So I mean, and it's exactly the result that you use, because it's the same majorization based theory, right?
Oh, right. So this is clearly something I wasn't aware of. So basically, you say that. So if I remember,
that you don't. So what you are doing is you are let's say blurring the catalyst, but you as well there are different alternative. I mean, I'm not saying there's anything wrong. I'm just saying that there's an alternative approach when you blur the final state, and in both cases you can recover the second laws with a different interpretation. In one case, you basically say in macroscopic theory you don't see the difference being like epsilon 10 to minus 15 because you don't have the resolution to do this. In the other, you say, well, there is always other states lying around. As you've shown, any state can be a catalyst. So many states allow you to perform it. So those are two different, I'm not saying anything is wrong. I'm just saying that there are two different paths. And maybe when you motivate your thing, you shouldn't disregard the other path, because it also works there.
Sure, yeah. So that's a very good comment. I wasn't aware of that. So yeah, so definitely.
Okay, fine. Thank you.
Okay. Yes.
Yeah,
Thanks for discussion. Yes, one more question. Pavel, yes?
Okay, so just quick question, because I see in your scheme that you have kind of two independent buffs, right? Buff states. Is it correct? So, I mean, is it legal in physically speaking, in physical situation? Because when you have this final network, right? You have this network with those U's, yes. So basically, usually we feel like we in physics we have single buff, okay, with temperature. So here you have the two independent. I kind of guess that you get some correlations at the end, okay, between them. Mm-hmm. So I understand this is kind of maybe not a weakness, but kind of a little bit of drawback in the scheme, right? From the physical perspective, and mathematically it's interesting. I mean, it's a very nice result. I like it, but how would you comment the physical aspect?
Yeah, so if I can briefly elaborate on that. So basically, the fact that we have here those two heat buffs apparently. So I use it just to present this graphically. But the idea is that we still have one single heat buff in the background with one fixed temperature. And so what we generally allow for in those resource theories is that we are able to take free states from that heat buff, from the heat buff at no expense. So basically here, what we do is we take two states from the heat buff.
Right. So this is kind of when you have many. Yeah. Okay. So in this regime, of course. Yeah. But by the way, do you know anything about the correlations in them?
Right. So yeah. So one thing is it was quite interesting when we were thinking about this. So basically, it's quite important that you keep the correlations with at least with respect to this bottom, let's say, buff state. If you kill those correlations here, then then basically you are not able to reach this sub-exponential type of error. So if you forget about those correlations here, so if you kill this, throw it away, and you take a fresh buff state here, then what you can show is essentially that the error is 1 over n, so it can't be better than 1 over n.
Yeah, so this is crucial that you really take this instance and not another one. Okay,
right.
Thank you very much.
Thank you very much. Are there any further questions? Maybe a last short question? Well,
if I can, then I will have one.
Yes, please.
Thank you, Patryk, for the talk. This is a remark that can be turned into a question. So do I remember correctly that once you told me that there were exceptions from your theorem for thermal operations, like when you start from a pure state in the ground state, for example, then it cannot be a catalyst, and it does not matter how many copies of it I have.
Right. So I would say that this corresponds to the case when your catalyst, your omega, is a thermal state. So if it's a thermal state with the temperature beta, so which we have in the background, and basically, so at least if you look at it mathematically, then it should work. But what it really is that, in fact, to make this statement mathematically formal, what you have to do is to. So I was saying that if you have a sufficiently large number of copies, but in fact, what the mathematically correct statement is that there is some n0 such that when n is bigger than n0, this transformation holds. And in the case of thermal states, when omega is a thermal state, then this n0 is infinite. Basically, you don't get this. You will never be able to perform this transformation. And maybe to see this more physically, then this unitary U, which somehow has to encode the information about the transformation in this D1 state, then you can never produce such a state using any. So if your omega is a thermal state, then basically this unitary would have to increase. So it would have to decrease the entropy of those combined systems. But it will never be able to do that because it's a unitary. So
Fine.
Okay, thank you.
So let us thank the speaker again. Thank you very much for your short visit to Poland, to Krakow. I'm sorry we cannot have not time for a longer discussion, but now